Hello and howdy everybody, and welcome back. We're going to be moving into the more difficult of the Apollonian problems, in that we're done with points. No more points. Not that we're not going to be seeing points as we do things, but our given objects, none of them are going to be points. So we've got line, line, and circle. That's the one we're going to be doing today. Line, circle, circle is still left to go, and of course just 3 circles, which is the problem of Apollonius. And I didn't, make reference to this when we did line, 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 because line, line, line's just in circles and X circles. But as soon as we start dropping points and having circles around, we can introduce a very, very interesting technique, which I call sort of radial reduction, to the mix. And I'll be mentioning it in the next 2 videos as well, although probably only briefly for CCC, because that's going to take a while. But the idea is to imagine we had a solution to the problem, and then by extending the radius of because we're looking for circles tangent to things, by extending the radius of our solution or contracting it, we can see that what we've really got is just a solution to a much simpler situation. The technique of radial reduction basically lets you get rid of one circle, and we have finally one circle, but you're not able to have any points during the whole process. Okay, now line, line, circle, or LLC, is generally there are 8 solutions, but in this case I have a gripe with the use of the phrase generally. Because if I were to ask you to just draw 2 lines in a circle, you probably wouldn't draw your lines parallel, but you'd probably put your circle somewhere. And it would probably be in sort of one of these 4 quadrants, or if you're being a little more sassy, you might have it be over one of the lines. But I doubt very much people would put the circle over the cross point. And if you were to randomly generate lines and circles, I very much doubt that this would come up a whole lot. I tend to think that this is far more specific than something like this, or like this. And so, while yes, the most you can get is 8, I think in the wild you would probably encounter something like this, which I believe has 4 solutions. Okay? But I'm going to show you how to do the big general 8-thing solution. And what we're going to have is basically a circle in here, a circle in here, a circle in here, a circle in here, and then a circle out here, and a circle out here, a circle out here, and a circle out here. Whereas if our circle is stuck in one of these quadrants, you can only have... I shouldn't have made all these circles, now I have to delete them all. You're sort of limiting yourself where the circles can come from, or where the solutions can come from. And so when you do the radial reduction, you essentially reduce to point and 2 lines, which has 2 solutions, and you can sort of beef that up to 4 solutions, but having your circle over the point intersection is usually, I find, the best way to construct 8 solutions fairly quickly. And it's also the easiest way to see where you get 8 solutions. 2 solutions per quadrant, essentially. Okay. Now, there's actually, I found there's sort of 2 ways to approach this problem. One of them is to reduce it to point, line, line. Another one entirely is to reduce it to point, point, line, so PPL. Both of them are perfectly fine. They're perfectly acceptable. You can find them both up online. But I think I'm probably going to do point, point, line to make the video as short as possible. Also, I think it's fairly obvious to reduce it to point, line, line, but a little extra geometry reduces it to point, point, line, which I find easier just for me to remember and do quite quickly. But I've been talking about this radial reduction, or I've mentioned it a couple times. What does it actually mean? Well, suppose I had a solution. I'll make it a nice little internal solution. There we go. So he's on the circle. There. So suppose I had a solution to my given problem, the three pink objects, the 2 pink lines, and the pink circle here. Well, if I were to sort of actually, the picture will probably go a little better if I do an externally tangent one. I think it's easier to understand this way. So I have a solution to my line circle. Okay, we'll just ignore this for a second. There we go. All right, so roughly I have a solution there. Now, what happens if I were to increase the radius of this circle by the radius of my given circle? Increase the radius of the purple circle by the radius of the pink circle. Well, I would, because we extended out by a radius, the new purple circle, and I'm going to change the purple to red because that's what we've been using for solutions. So the red is a solution. If I were to create a new circle, expand it out now it's been expanded by a radius. It passes through a point, but it sort of intersects these pink lines here. Never fear, because if I were to, since we've increased the radius by, what do we want to do? So it's tangent to these 2 lines. That means we get right angles here. And if we then extend outwards, we've sort of just gone exactly a distance of the small radius, the radius of the pink circle out in both directions. So we're not tangent to our pink lines anymore, but we are tangent to 2 brand new lines, which are parallel to our original pink lines. So if for a moment we hide all this fun stuff, and we say instead that we'll use some colors here. Orange, I think, probably stands out. There we go. And we'll make the lines orange as well. So if we can, and we can create this orange line pretty quickly. How do we get this orange line? We just shift our pink line over by the radius of this pink circle. These are all given amounts and lengths and lines that we can work with. But if we say, gee, let's solve the orange line, orange 2 lines 1 point problem, and we get this sort of, what would you call that? Beige or maybe salmon maybe? It's near the pinks in the color palette, but you know, we get this big circle as a solution to our point and line problem. Well, we can shift everything over and get a solution to our pink lines and pink circle problem, just by reducing the size of the salmon-colored circle. Okay, so knowing that a solution to the orange lines and point problem directly translates to a solution to the pink lines and pink circle problem, we can get, and that there's this nice back and forth, we can set up these orange lines and this orange point and start solving it, the point line line situation, which is something we've already seen before. We're reducing the problem by reducing the radius of our circle down to a point. Okay? But because we reduce the radius of the circle down to a point, as a result, we have to start shifting these lines. And we shift them away, we shift them close, but lines can be shifted by an amount. Whereas if I had a point somewhere in this problem, I can't really shift this point in a special direction based off this radius. All I could do is sort of puff him up to a circle of that radius, and that wouldn't really help. So that's why you can't have any points. You just need to have lines and circles to do this sort of work. Okay, so that's the idea. Now, this actually is the center, but these are not appropriately shifted lines. Okay, and so you can do the 2 lines and a point method that way, but I'm actually going to show you how to do it with 1 line and 2 points, because it's just an extra bit of fun geometry there as well. Okay, what do I need to do? Let's shift our lines. And we're going to shift them by the radius of this circle in sort of two different directions. So we will connect these random points on the pink lines, and we're going to create some parallelograms. There we go. So now we have the radius length reproduced, and these shouldn't be orange. These should be blue. We'll make them the nice blue color. So now I have the length of the radius of my pink circle. And now I have two circles that are identical. And we'll drop the perpendicular line tool. And that gets me these points. And now back to the parallel line tool. And these guys can be orange. There we go. So it looks like a mess, but let's clean it up, and we'll know what we've done. So we copied the radius of the pink circle. And then we used that copy to create a circle at just random points on the pink lines, but we were able to extend the pink lines out in both directions by the radius of the pink circle. Okay, so this is our setup. And now, if we wanted to, we could select all the pink stuff and ignore it. And come on. There we go. Ignore it and now try and solve this problem with this point and, this pair of lines, this pair of lines, and this pair of lines, and this pair of lines. And each point and pair of lines will give us two solutions. But we're actually not done yet. Okay, we can do a little bit more with setup. And I'm also going to keep the pink solutions here just so we are reminded of what we're shooting for. And basically, once I hide something, in order to get it back, and once it's deselected, I have to select everything, and it's a nightmare. So we got the center here. Notice that as I move it around, these translated lines don't change at all. Okay. So what are we going to do? Well, if we think back to point line line, which is not actually the solution that I'm going to be, the simpler case that I'm going to be reducing to, we use angle bisectors. Okay, because any circle that is tangent to these two lines is going to have to lie on that angle bisector. Okay, and actually the same for some of these other lines as well, these pairs of lines. Okay, not all of them, but some of them. So what we're going to do is we're going to use this fact to our advantage. And, if I have a circle that's, say, tangent to these guys, and this, the center of our given pink circle lies on that, that circle, that solution, the thing that's tangent to our pink lines, then if I reflect this center line, in fact, if I reflect this whole circle in our angle bisector, then I get, then that center will have to lie on this circle as well. And we'll show that, reflect about a line, reflect this guy in a line, and what do you know? He lies on this circle still. Okay? And this is a nice and useful technique. As I move my circle, the center, if it stays on the purple circle, we have a second point that's on this circle as well, this purple circle. Okay, and I've talked about how to use straight edge and compass to do reflection in a line, so it is something we can easily take advantage of, and we will. So, don't need this reflected point right now. But what are we going to do? Well, we're going to reflect our center point, which is a point, because we're doing point line. We need a second point to work with here. we're going to reflect it in the other, the angle bisectors. Okay, and because of where we are, because our circle is sort of right here in the middle, if our circle was really far away, this second angle bisector here, or second reflection about an angle bisector over here on the left, would be too far away to do any circle passing through those 2 points would not play nice with these orange lines. But if I pull them close enough, yeah, everything sort of works out. Okay, so that's what we're going to work with. So now we take our original center, because we need that to lie on our sort of salmon-colored solution, and the reflected point will produce a second point that we can use. And now we just start picking orange lines that we want to work with. Okay, so we'll just do point line there. So how do we solve point line? Well, we get the intersection, and I don't need these angle bisectors here anymore, actually. Okay, and I would like to remind you that you don't have to do it this way. You can just do a whole bunch of point line with this reduced point here, but I think it's a little nicer to work with this. And you'll see that it works out just fine, and I'm just a bigger fan of doing point line than I am point line. Okay, intersection, there we go. Now, there we go. And we get 2 intersection points with this line here. So now, and we'll use that salmon color. Point, second point, and point, second point. So now we have 2 of these salmon colored solutions. Okay. Notice that these salmon lines are tangent not only to the orange line that we were using, but the other orange line that works with the angle bisectors that I've gotten rid of. And the reason that this works, or that you get the same line here, is just because everything is reflected about the angle bisector, and that the angle bisector of these pink lines that we use to reflect and create this second point is also an angle bisector of these 2 orange lines. Okay, and had we chosen to use this other orange line rather than the one that we did use, we would get these same 2 circles here. Okay, so now, if I were to do something like shift, if I were to shrink, for example, this one salmon colored one here, which I will highlight in blue for a moment, if I shrink it by the radius of the pink circle, I will get something that's tangent to these 2 pink lines and this pink circle, and we'll see that eventually as well. We'll change it back to salmon color. Okay, whereas this one right here, if I shrink it, it's going to get further away from my circle. If I enlarge it, you can see where the smaller salmon one is. If I enlarge it, we just imagine puffing it up the size of our radius, we're going to overlap the pink circle. So it doesn't look like we're going to get a solution there, and that's okay. But line circle does get 8 solutions, but we've got more lines and more more lines and more point line stuff to be working with, because we've only used 1 line, and he had a little friend as well. But we can do this all over again, not use either of these 2 lines, but now use one of the other orange lines. Okay, and we still do point line, exactly the same way that we learned so long ago in those videos. No, I don't want it to be salmon colored because I don't want to get confused, so we'll go back to my standard purple. Go to our second point, intersection, there it is. And now we get 2 intersection points here as well. Okay. And now, come on, let me get the salmon color. There it is. So point, and we use these 2 second points. There we go. And this one here, if it's shrunk, it'll fit right inside the pink circle and the 2 pink lines. And then point, point, point. So if this fella is shrunk, it will also fit right between. Yeah, if this one's shrunk by that radius, then it'll be tangent to our pink circle and the 2 lines there. Okay. So, what are we to do now? So each of these 4 circles here will get us a solution. I know I mentioned this one, if I expand it, isn't going to work out, and if I shrink it, but if it's smaller than the big one here, and I think if well, you'll see the technique I use at the end, and this one does, I believe, give us a solution. Anyway, let's clean up. We're not done yet. We've got 4 potential circles. These are circles that are solutions to the specific line point problem, or point line line problem, depending on how you want to view it. But they are not yet solutions to our original problem. Okay, and we're not done looking at point line cases because we have this other point that was a reflection from an angle bisector. We need to use both of them in order to get all 8 lines. Okay, so we do the exact same thing that we've done all along. There we go. Extend them out. We just pick a line to work with, except now when we use this line, this orange line here, it won't be tangent to this other orange line. It'll be tangent to this one, based off the angle bisector that we reflected in. But everything's okay. And we're going to need to go back to purple, center, and perpendicular line with our second point, intersection, and we get some tangent points. There we go. And 3 points. 1. I gotta zoom in so I don't accidentally click that center of a circle. 2, 3. And then 1, 2, 3. And as I'm doing this, I'm double checking that this circle does go through the point that I care about, but is also tangent to these 2 orange lines. And it is. So we clean things up in anticipation of our very last, I suppose I could keep that line, our very last point line case. So we intersected with sort of the 2 bottom orange lines. Now let's intersect with the 2 top orange lines. So that's right here. Gonna have to create a new midpoint. There it is. Switch back to purple. Perpendicular line tool. Intersection points. Compass. And then we were using sort of this top left line. So there we go. And back to our salmon. Tangent point, second point, original point. Tangent point, second point, original point. There we go. So we have all our candidate salmon lines. We just have to sort of shrink them down. And we don't need our points reflected by angle bisectors anymore. So these circles give us solutions to various point-line-line situations. But we want to solve the pink lines and circle Apollonius problem. How are we going to do that? Well, we reversed the process. We shrunk everything down. We shifted things by the radius of our circle. Now we're just going to reverse that process. Okay? So the easiest way to do this, just pick one of the circles. When we shrink it, it's going to stay concentric, so it'll still have this center here. But now, if it's going to be tangent to this pink line, it'll have to intersect at a perpendicular line, so we can use our perpendicular line tool. Get the point of intersection there. And now we're just going to be dealing with solutions, so we'll go with the traditional red. When I connect it up, look at that, it's a solution. It's tangent to both our lines and even our pink circle. So there we go, we can get rid of our helper points and our salmon circle, and we just do this with all of them. Doesn't matter which line we choose. Get our intersection point. There we go, second solution right there. And I tend to go from biggest to smallest, so while we're out here, we'll get this one down here. Incidentally, we don't need any of this orange stuff anymore. Okay, that was just helpers. We've already solved the problems there. There we go, tangent to the circle and the lines. Now we'll zoom in a little bit. Now, what about this this small circle that I said? You know, if we contract it, we're going to have a problem. If we expand it, it's going to overlap the lines. Well, if I contract it by the radius, its radius is smaller than the pink circle's radius. So imagine that it had a negative radius, but there's no such thing as a negative radius. If you are on one side of a circle and you go towards the center by a length equal to the radius, you're at the center. If you go by another length, you're just sort of on the opposite side of the circle. So what we're essentially doing is, by reducing the radius of this small circle, we're sort of flipping it inside out. And because it's so small, it actually gets a bigger radius in terms of absolute value. That's the idea behind it, at least. But as I noted earlier, visually it does not look like it's going to give us a solution. But watch. Watch and you shall be amazed. Behold. It did. It sort of, if I can sort of rewind that. So we're at this this radius right here. We shrink it. And as we shrink, oh, it gets smaller, it's smaller, it's smaller, it's smaller. But we've only subtracted its much smaller radius. We need to subtract the radius of the pink circle. So we keep shrinking, but we emerge on the other side. Keep shrinking, keep shrinking, keep shrinking. And then once we finally shrunk enough, there it is. Alright. Hit Control-Z too many times. Let's put that back there. There we go. So it really did give us a solution after all. Unlike, I was a little speaking too fast, because when we do this reduction technique for the harder two cases, is it two left? I think we've got two things left. Yeah, we've got two circles in a line and three circles. When we reduce with those ones, what's going to happen, and you'll see this eventually, is that some of the circles, these salmon circles, these candidate circles, these test circles, they won't, when we shrink them or resize them, actually produce solutions. About half of them get thrown out. And it's been a while since I had to do this one. I knew this happened with the reduction technique. I just could not remember that it doesn't actually matter for this one. But it matters when you have more than one circle. And you'll see that in the future videos as well. So just keep going on here. intersection, and boom, tiny circle. So this one is another circle that was smaller than the pink circle, and so when we shrunk it, its radius actually bounced back from just a point. There we go. 2 more to go. You can already see we've got 6 solutions here. Ooh, this is going to be a tiny one. But we got 6 solutions here. We're going to get 2 more in a second. We really do have 8 solutions, which is the best we can do. And it makes sense that we couldn't do any better because the circle, circle, circle problem only has 8 solutions, and that's the most general of the problems there is. I mean, you can technically view a point as a very special circle in that it has radius 0, and a line itself, we don't often talk about this in math, but a line is basically a circle with infinite radius if you view it in just the right way. So these special cases here are really just situations with circles that have very particular and very weird radii. Okay, but the general solution, the most general of them all, is 8 solutions for circles with just random finite radii. But there we go. And just as I predicted, we had some circles on the outside and some circles on the inside. And we can sort of move it around a little bit. But we get our solutions. And depending on where the center of this circle lies and where those sort of reflected, what do I want to say, the secondary points that we created that were reflected in the angle bisector of the pink lines, depending on where our center moves, sometimes we can't solve the point-point line situation because the line ends up dividing things or whatever. And you know, some of this is also just GeoGebra is a bit temperamental. I've complained about that in the past, but you'll notice that, especially over here, with a circle just in one quadrant, we do not get all 8 solutions. You can get 4 solutions there, though, although I don't know why they're not popping in. That's okay. Mysteries for me to solve on my own, but there we go. We're back to 8 solutions. So this is the first of our 8 solutions. Line, circle, circle is going to have 8 solutions, and of course, the 3 circles, CCC, which is the crowning achievement of this whole process, will have 8 in general as well. There we go. And hopefully you guys enjoyed that. And if not, I hope you enjoy the next one, because I think the line, circle, circle is pretty nifty. It takes a while, but I think it's pretty nifty as well, because it reduces to point, line, circle, and that further reduces, and it uses a whole lot of the stuff that we've already seen. And I will see you guys for that video next time. Have yourself a nice day.